Welcome to The Explainer. Today, we're going to absolutely shatter our standard flat grid perception of reality. We're diving headfirst into the underlying mathematical architecture of the universe itself, using Manfredo P. Ducarmo's foundational text, Riemannian Geometry. Buckle up because we're about to explore the true blueprint of space.
Okay, I want you to take just a second and think about this. How on earth do we measure a space that curves in dimensions we literally cannot see? It's a wild thought, right? This exact question is what drove brilliant mathematicians like Bernhard Riemann to invent an entirely new language for the warping fabric of space. You see, our brains are hardwired for rigid, three-dimensional boxes, but true differential geometry, it's a beautifully dynamic, bending reality.
So, to build this conceptual geometry, we've got to start with our foundational building block, the Riemannian manifold. Basically, think of the Earth. If you're standing in a field, the abstract grid around you feels completely flat. But zoom out into space, and obviously, it's a globally curved sphere. A Riemannian manifold works exactly like this, except it's equipped with a rigorous metric, basically a mathematical compass that lets us precisely measure distances and angles at every single point across any number of dimensions. It's almost like having a universal GPS for hyperspace.
All right, here is our roadmap for today. First, beyond flat Euclidean space. 2, manifolds and tangent spaces. 3, geodesics, the shortest path. 4, the mechanics of curvature. And 5, universes of constant curvature. Let's get right into it.
Section 1. Beyond flat Euclidean space. Time to shatter that illusion of a perfectly straight universe.
Moving right along to Section 2, manifolds and tangent spaces. This is where we ground all that abstract math into something we can actually calculate.
As Ducarmo formally states, this vector space is called the tangent space. Think of it as our mathematical anchor. It gives us an n-dimensional grid where all our standard linear operations work flawlessly, completely ignoring the surrounding curvature. Literally, it lets mathematicians freeze a warped space at a single point, crunch the calculus, and then stitch those flat planes together to comprehend the entire massive structure. It's kind of like rendering a 3D video game environment using millions of tiny flat polygons.
All right, Section 3, geodesics. Let's talk about finding the absolute shortest path.
So the crucial takeaway here is that moving along a geodesic maintains a constant geometric energy. It behaves exactly like a particle just gliding effortlessly through a frictionless void. It isn't forced to speed up or slow down, it simply follows the natural, unforced contours of the space it's in. Imagine the mathematical equivalent of just coasting perfectly downhill forever.
Which brings us to Section 4. The mechanics of curvature. This is how we actually measure these unseen bends.
The text hits us with this incredibly dense definition. Curvature measures the non-commutivity of the covariant derivative. Okay, pretty wordy, right? Let's visualize this on an abstract grid. Imagine walking in a tiny loop in a warped space, but you're keeping your arm perfectly straight, keeping your vector strictly parallel to itself the whole time. Because the space itself is bent, you will actually end up pointing in a completely different direction when you return to your starting coordinate. And that exact discrepancy, that, my friends, is curvature.
Let's contrast these two realities. If you do that same loop walking trick on a flat, normal Euclidean grid, your arm points the exact same way when you get back. The curvature equation perfectly zeroes out. But in a Riemannian space, the curvature tensor, represented by that r, measures the exact unseen deviations from flatness. That tensor is literally the mathematical master key to unlocking the true shape of the space.
Now we can actually break all this dense tensor math down into a neat little hierarchy, zooming all the way from the massive curvature tensor down to a single number. The curvature tensor holds every single piece of geometric data. Too complex? We drop down to sectional curvature, which isolates just a two-dimensional slice. Still need a broader view? We calculate the Ricci curvature, which averages across those planes. And finally, we distill the whole shebang into the scalar curvature. That's a single, elegant number summarizing the total warp at that precise point.
Almost at the finish line, Section 5, universes of constant curvature. Let's look at perfectly symmetric spaces.
So what exactly happens when a space lacks all those random bumps and valleys and just curves identically everywhere? Well, as Do Carmo writes, we give this highly uniform geometry a special designation, a space form. These are without a doubt the purest, most pristine, and incredibly symmetrical environments in all of differential geometry.
This categorizes the three fundamental types of mathematical universes based entirely on their uniform curvature. If the curvature is exactly 0, boom, you have our standard infinite Euclidean grid. If it's uniformly positive, the grid actually closes in on itself, forming a finite sphere. But what if the curvature is negative everywhere? The space expands outwards infinitely and exponentially, forming what we call hyperbolic space.
Which leaves us with one staggering final thought. If perfectly uniform mathematics can dictate the entire shape of abstract universes, just how deeply does this blueprint govern the unseen curves of the physical cosmos we actually inhabit? I mean, are we floating through a flat, positive, or negatively curved universe right now? The beauty is, differential geometry gives us the exact mathematical machinery to eventually find out. Thanks for joining me on this explainer through the incredible abstract architecture of space.